Hi, and welcome to the talk of our paper Aion, enabling open systems through strong availability guarantees for enclaves. My name is Fritz Alder, and this is work I've done together with Jo van Bulk, Frank Piesens, and Jan Tobias Mühlberg. We're all from the KU Leuven. Now, the core motivation for Aion is for embedded systems. And in embedded systems, or in conventional embedded systems, you have this high-level overview where you may have some hardware that runs some real-time operating system, and on top of that there is an application running that may access one or multiple peripherals. Here it could be a sensor and some network where the sensor data is reported to. Now, we envision that in more modern situations you may have this situation where you not only have application 1 anymore, but you now also have application 2 or any other amount of other applications that may want to access the same set of resources, the same set of peripherals as application 1. And with this new model where you have multiple applications, you now have a model where application 1, and from the perspective of application 1 here, application 1 may have to trust not only the hardware, not only the operating system, but now also other applications if it wants to look at its security, but also at its availability guarantees. So let's say application 1 has the desire to read the sensor once every second and send out an alert. In order for this to be possible, application 1 actually has to trust application 2 to not disrupt its availability in this sense. And the problem with this in these real-time operating systems can be that monopolizing such a system resource or stalling the CPU is often possible. Very often you have a cooperative scheduling system where hackers would not take part, right? Hackers would not cooperate if they want to disrupt this system. And even postponing deadlines of application 1 could have harsh consequences for the guarantees that application 1 wants to provide in its execution context. Now, we specifically look at the situation where application 1 and application 2 have a similar set of guarantees. So application 1 and application 2 here are seen as equals. There is no strict priority or preference we can give one over the other. Instead, we assume that application 1 and application 2 are expected to be treated equally and fairly from the side of the operating system. And you can think of this as a sort of cloud computing equal, right? Where remote parties provide this application and expect it to be scheduled by application 1, by the scheduler and by the operating system, and application 1 and application 2 are to be treated both fairly and equally. And in this situation, what we would want from the system is this situation, right? A situation where application 1 does only have to trust the hardware. Maybe we could add some software components that are very fine-grained or small, but ideally, application 1 would not have to trust application 2 anymore. And we at KU Leuven have been working on TEEs, trusted execution environments, for some years now. And so the natural question from our end is, can we somehow do this with TEEs? Now, trusted execution environments, for those of you who are not too familiar with them, are basically this metaphor of a castle inside the processor. Anything that is residing inside the castle is protected from any access from the untrusted outside of the castle. And anything that happens inside the castle cannot directly be seen or interacted with from outside. The only access with this castle is through strictly defined gates and through strictly controlled entry and access interactions. Now, this is how enclaves work. So enclaves are basically such a castle, and you can spin them up and say, look, this program is now protected, and I have this input and output operation with the enclave, but nothing else can happen except these strictly defined accesses. And that works great for confidentiality and integrity, as you could think. So if we just look at spatial isolation here, application 1 is already protected from the OS, from application 2 in regards to spatial isolation, which is confidentiality and integrity. But for availability, this does not work. So availability can also be seen as temporal isolation, where the shared resource is time. And there is no temporal isolation guarantees with enclaves. So application 2, as we have seen in the slides before, application 2 can always disrupt or stall or not cooperate in any scheduling system. And this would have impacts on application 1. And it could mean that application 1 would not be able to keep its deadlines. Now again, of course, if you have strict priorities between them, the operating system and the scheduler can always say, I schedule application 1 before I schedule application 2. But that's, let's say, the easy case here, right? The difficult case in this scenario is what happens if we cannot apply this priority, and what happens if we have to see the application 1 and application 2 should get a fair share. Now, that's why we designed Aion. And Aion, in short, is a security architecture that extends TEEs with guarantees on enclave availability, even if we have very strong software adversaries on the system. So even if, let's say, application 2 is actually malicious. And in Aion, progress and real-time guarantees can be offered to a number of applications of the same priority. And we do this by decoupling the spatial isolation guarantees from the temporal isolation guarantees. So we decouple the availability from the confidentiality and integrity guarantees. And I will later show we have a prototype implementation with the Riot OS and with Sancus. Now that's the basic architecture. And we have 4 building blocks that I will go through now. There is the base TEE, there is an exception engine, an atomicity monitor, and all of this are in hardware, and they enable a software scheduler that also runs inside an enclave. So for the TEE, we build on existing TEEs. There is no need to reinvent these for isolation, for attestation, and for dynamic enclave deployment. But very importantly, any violations, for example, if protected memory is attempted to be read by an untrusted program, these violations should not reset the system, because then we lose our availability again. These violations have to be handled with carefully. And this careful handling is done by the exception handler, or by the exception handling mechanism in the hardware engine. And the idea is that we securely interrupt these enclaves on violations or on interrupts, but we do not trust software handlers with our data. So the handling of the current CPU state is done in hardware, context save is done in hardware, and the context restore is then done on software on the resumption. And then we make sure that after this exception has been handled, in the sense that the context save has been done, we jump to a strictly defined handler that is defined on the system platform. And lastly, in hardware, we make sure that we do not allow atomicity. Now, that's not so great, as you could think, because we always need some sort of atomicity. And that's why we add a certain notion of bounded time periods where we'll do allow atomicity. So we introduce the clicks instruction that allows you to disable interrupts for X cycles. And after that, interrupts will be automatically triggered again. So this means that no application can disable interrupts completely. Now, the last step is the scheduler. And we develop this one in software, and we protect it via an enclave. We do ensure that all interrupts on the system are handled by the scheduler. And lastly, we do allow the scheduler to be the only entity on the system to disable interrupts completely. So the scheduler is in complete control over the platform availability, and we do have to trust it as the single software entity for our availability. Now, all of these specific design decisions mean that the scheduler can now perform guaranteed scheduling for dynamic enclaves, even in presence of software adversaries. We did implement a prototype implementation of this with the Riot operating system for the RTOS and Sancus SETEE. Sancus is a 16-bit MSP430 open hardware implementation that we did here at KU Leuven some years ago. And we extended it now to also include a sort of exception engine and this atomicity monitor. All of this is open source, and I will show the link at the end of the presentation. Now, what can this prototype do? Let's take a look at the case study that we also had in the beginning of the presentation. Let's assume two simple applications, application 1 and application 2, that each have deadlines at which they want to run. And for this, they each set a timer with a scheduler, at which the scheduler is woken up and scheduled application 1 and application 2. Now, we assume that there is an attacker also on the system that will just consume up as many cycles as he can. So here in this case, the attacker would be scheduled at all the other times as application 1 and application 2 are not scheduled. And this would, for example, simulate application 3 that would also try to get some guarantees from the scheduler, or just any attacker that may compromise other threads on the system, or any variety of attacks in the middle. Now, with these timers and with these set deadlines, that's application 2 and application 1 set, here we have a guarantee that after the deadline and after the timer in this sense triggers, the application is scheduled roughly 2000 cycles after the deadline occurred. So in this very simple scenario where the attacker just tries to use up cycles, will then be interrupted by the scheduler and will then, where the scheduler will then schedule application 2. This would roughly mean that there is a delay of 2000 cycles that can be accounted for. But what happens when the attacker actively tries to postpone the deadlines and actively tries to maliciously tamper around? Well, the worst case attack for us here in our prototype, but with the hard upper bound guaranteed by the hardware, is the following attack. The attacker will attempt its own atomic period, so the attacker can do its own click cycle of X cycles, and it will try to do so by starting this cycle right before the deadline triggers. So right before any of the deadline, or right before any of the interrupts that would jump into the scheduler happens, the attacker will start its own atomic period. And at that point, right before this atomic period ends, so roughly around this time, the attacker will jump into the scheduler with an operation like sleeping or like retrieving a time. In this specific sense, the longest operation in our system that the attacker can do is trying to sleep. This means then, in our implementation, that the scheduler would first process this request. And because the scheduler does not interrupt itself, and because the scheduler is non-interruptible, this would mean that first this request would be handled, and then the scheduler would process the pending interrupt that happened before, and would only then jump to application 2. So this situation is where the attacker fully makes use of his capabilities of the clicks and of operations on the interactions he can himself perform with the scheduler. And this is a little bit of a crafted attack, and it's of course always system specific and implementation specific what this attacker can specifically do for this worst case attack. But the most important part is that no matter what the attacker attempts, this will always be bounded by the hardware, in addition with the specific scheduler implementation, by roughly 7,000 cycles. And of course, you can move this up a little bit, move this down a little bit, depending on what the scheduler is performing. But it's very important to focus on the fact that here we have a hardware guaranteed upper bound, or hardware and software co-design that guarantees an upper bound on the time when application 2 is triggered. Now that's great. Upper times and interrupted arrival times are very useful, but at the same time, it is not trivial to go on from there. So it is not trivial to also guarantee something like progress. Because once the handling job starts the execution with its own atomic period, it also wants to have some notion of progressing in its execution. And right now we can only guarantee this progression with the clicks bound. And the problem with this progress is definitely that if we increase this clicks bound, so if we allow applications more than this 1,000 cycles, the attacker will also gain the same amount of cycles as a bonus, right? So that's definitely a limitation of this attempt, because whenever you want to increase this progress time of an application, you will also increase the interrupted arrival time of the applications. This concludes my presentation of Aion. In short, Aion extends existing TEE architectures with an exception engine and an atomicity monitor. And this allows to create protected schedulers in software. And our implementation of it provides deterministic scheduling and trusted time, even in the presence of strong software adversaries on the system. Aion can guarantee interrupted arrival latencies of roughly 7,000 cycles. And at 20 megahertz, which our boards are running on, this is roughly 346 nanoseconds, so it can be seen as a very short time. The full source code is online. We have implemented this on the Sunquist TEE and on the Riot operating system. And the full source code is on GitHub, and you can play around with the code. And if you're interested, feel free to reach out to us via GitHub or via email, and we're very happy to help you run this on your system. This concludes my presentation. Thank you very much for listening, and I'm very happy to respond to your questions.